Hi, this lecture is about the visible light spectrum, okay, electromagnetic waves, and the different colors in the visible light. So the first is to talk about the electromagnetic wave, okay? An electromagnetic wave is the perturbation on an electric field and a magnetic field through the space. Okay? So to understand current atomic theory, you need to know about the electromagnetic radiation, also called electromagnetic energy or radiant energy. Visible light, X-rays, radio waves, and microwaves are some of the types of electromagnetic radiation. All of these consist of energy propagated by electric and magnetic fields that increase and decrease in intensity as they move. Yeah, through the space, or can be through different types of materials. For example, air or a solid or water, for example, okay? The electromagnetic wave can pass through different materials, not only the empty space. This classical wave model explains why rainbows form or how magnifying glasses work, and many other familiar observations. Okay? But it cannot explain observations on the very unfamiliar atomic scale. Okay? In this section, we describe some properties of electromagnetic radiation and note how they are distinguished from the properties of matter. But we will see that some properties blur the distinction between energy and matter, require a new model to explain them. Okay, so look at this. Look at the picture here about the speed of light. Okay, the electromagnetic spectrum is formed on different types of radiation. Start, for example, with the radio type. Okay, the radio waves are huge. Okay, they can have a wavelength about the size of a soccer field. But at the opposite side of this chart, for example, we can find the gamma rays. Okay, the gamma rays are a type of radiation, or is a type of radiation like the size of a subatomic particle. Okay, gamma rays will have a lot of frequency. Look at this. There is a lot of frequency right there. Opposite to that, for example, the radio waves. The radio waves will have a lot. Will have a big wavelength, but the gamma rays will have a big frequency. Okay, so the electromagnetic spectrum is the range of all types of electromagnetic radiation. Visible light has wavelength in the range of 400 to 700 nanometers is what you can see with your eyes. Okay? A wavelength is the horizontal distance between the two peaks of the wave. Light is measured by its wavelength. Okay. So the electromagnetic waves are categorized according to their wavelength and frequency. The classification determines if the electromagnetic radiation sits to the left or right of the visible spectrum. And this is very important. Look at this. A long wavelength will be a low frequency. And yeah, of course, a low energy. So the red color has a low energy. On the other side, we will find the short wavelength, but at a high frequency. And it's the blue color, okay? Blue color will have a high energy. Okay, this is very important. So visible region is between the 400 nanometers and the 750 nanometers, okay? You can find that wavelength, the red color. And look at this, the visible spectrum is just a part, is just a component of the entire electromagnetic spectrum, okay? Next to the visible region, we can find the infrared, okay, and the ultraviolet region, okay? So yeah, ultraviolet region will have more energy than infrared region, okay? Excellent. So if we want to talk about the wave nature of light, the wave properties of electromagnetic radiation are described by 3 variables and 1 constant, okay? So the first is the frequency. The frequency of the electromagnetic radiation is the number of complete waves or cycles that pass a given point per second, expressed by the unit 1/2, also called hertz, okay? An FM radio station's channel is the frequency in megahertz at which it broadcasts, okay? So yeah, in a radio antenna, the frequency of oscillations of electrons on that antenna, okay, is the frequency of the radio waves that we can put on the radio on your car, for example. Okay, the wavelength is the distance between any point on a wave and the corresponding point on the next crest or throat of the wave. That is the distance the wave travels during one cycle. Wavelength has unit of length, such as meters, or very short wavelengths nanometers, for example, picometers, or non-SI units like angstroms. Number 3 is going to be the speed. The speed of a wave is the distance it moves per unit time, meters per second, okay? The product of its frequency, the cycles per second, and the wavelength, meters per second. So the units for speed of wave is going to be meters per second. In a vacuum, electromagnetic radiation move at 3 by 10 to the 8th exponent, okay? So that is a huge velocity. It's a physical constant that is called the speed of light, okay? And the speed of light is a multiplication of frequency and wavelength. And 4 is the amplitude. The amplitude of a wave is the height of the crest or depth of the throw. For an electromagnetic wave, the amplitude is related to the intensity of the radiation or its brightness in the case of the visible light. Light of a particular color has a specific frequency. But for example, on this figure over here, shows that its amplitude can vary. The light can be dimmer, okay, a lower amplitude, less intense, or brighter, higher amplitude, more intense. If we go back to the frequency, look at this. We have 3 different types of waves. And the frequency of the red one is gonna be the half of the frequency on B, and 1 divided by 4, the frequency on C, okay? So if you increase the frequency, you will increase the number of, for example, crests. Yeah, the number of crests, the number of the maximum point will be increased. The number will be increased. Okay? And yeah, of course, the visible light spectrum, the visible light is thanks to the reflect of that light through a surface, okay? But the black objects absorb all colors of light, and no light can be reflected, okay? And yeah, each color, or sorry, each element can, each element can has bright with a different color when it burns, okay? So, for example, on the fireworks, red, the red color is thanks to the strontium element. And you can see on this chart, red, orange, yellow, green, blue, purple, silver, and white is thanks to the burning on a different element. Yeah, for example, very common is yellow, thanks to the sodium, okay? Or, for example, purple, that is copper and strontium, okay? So each element can burn on a different color when, for example, it blows on a fireworks, okay? So let's see this video over here. about wavelength and wave motion. Okay.
Ever seen a Mexican wave at a sporting event? The effect is a pretty cool display that goes all around the stadium.
Oh, sorry.
Ever seen a Mexican wave at a sporting event? The effect is a pretty cool display that goes all around the stadium, but no one has had to move seats. All waves can transfer energy from one place to another without transferring any matter. This is done by a series of disturbances or vibrations that carry the energy. Just like the people in their seats, only moving up and down when it's their turn. Waves can transfer energy through solids, liquids, gases, and empty spaces, otherwise known as vacuums. There are two types of waves, which we look at in more detail in another video, but the basic features are the same. These four words describe different properties of waves. Let's discover what each one means. The frequency of a wave is the number of complete waves passing a fixed point in a given amount of time. This time period is usually 1 second. This is what one complete wave looks like. So if this was our time period, the frequency would be 5. Frequency is given the symbol F and is measured in units called hertz. Hertz measure how many complete cycles per second. So how many people in our Mexican wave stand up every second. The frequency and period are often confused. The frequency refers to how often something happens, whereas the period refers to the time it takes to happen. The period of a wave is the time for one complete cycle, so the time taken for one person to stand up, wave, and sit down. This would be measured in seconds. When something happens repeatedly, we say that the event is periodic and refer to the time for the event to repeat itself. The period of the Earth to orbit the Sun is 365 days. The period of a day is 24 hours. The period of a typical class at school is 45 minutes. Now for wavelength. The wavelength is the distance between a point on one wave and the same point on the next wave. For example, 2 peaks or 2 troughs. Wavelength is given the symbol lambda from the Greek letter and is usually measured in meters. Wavelengths can vary hugely in size. X-rays are very short, visible light is here, and FM radio waves are much longer. So we've looked at the frequency, period, and wavelength so far. Let's finish with amplitude. As waves travel, they create disturbance. The amplitude of a wave is the distance from the maximum disturbance to the undisturbed position. Think of a very flat sea, and then an incoming wave. The amplitude is the height of the top of the wave from the flat sea. Can you add the labels to these waves and work out the frequency? Notice that the top one is distance and the bottom one is time. Pause the video, work it out, and click play when you're ready. Did you get them right? In another video, we'll be looking at wave speed equation and connecting wavelengths and frequencies. For now, you just need to know what these 4 key words mean.
If you liked the video, give it a thumbs up and don't forget to subscribe. Comment below if you have any questions. Why not check?
Very good. And to finish this lecture, this is an example, okay? A dental hygienist, okay, use X-rays. So lambda is going to be 0.50 angstroms to take a series of dental radiographs while the patient listen to a radio station of lambda equal 325 centimeters and looks out the window at the sky blue. The lambda is going to be 473 nanometers. What is the frequency in hertz or inverse seconds of the electromagnetic radiation from each source. Assume that that radiation travels at the speed of light, 3 × 10⁸ exponent. Okay, so first step is the roadmap. Okay, you have the wavelength and a given units, Armstrong, centimeters, nanometers. Then, yeah, the first step is to convert Armstrong, centimeters, and nanometers to meters. Okay. And then use the formula of the speed of light and clear the frequency. That is speed of light dividing by the wavelength. So look at this. Each frequency or each wavelength is calculated on this exercise. And yeah, here we are doing the conversion of the wavelength in the formula. Yeah, I know. In class, I did it. First, the conversion, okay, of units, and then substitute on the formula. But okay, I will respect the order here of the problem solved, but it's the same. Okay, just try to look at the speed of light and the wavelength, divide these two quantities and find the frequency. Okay, and that's it. Look at this. The frequency of the X-rays, the frequency of the radio station or the radio waves, and the frequency of the blue sky. Okay, and of course, the biggest will be the frequency of the X-rays. So X-rays will have more energy than the radio waves and the blue sky waves. And that's it. Thanks. See you next time.